Bismillahirrahmanirrahim. Assalamu alaikum, dear students. This is Cambridge Physics 5054 course, and I'm your physics teacher, Mariam Rafique. Today, we're gonna discuss chapter number 18, and the name of the chapter is Current Electricity. Before getting into the core concepts of this chapter, I would like to share some learning outcomes so that by the end of this lecture, you will be able to calculate the net effect of a number of resistors in series and in parallel, describe the effect of temperature increase on the resistance of a resistor and a filament lamp, and draw the respective sketch graphs of current versus voltage. Describe the operation of a light dependent resistor and some assignment questions. Resistors in series and parallel. Resistors in series. When two or more resistors are connected end to end, they are said to be in series. The resistors could be simple resistors or bulbs or heating elements or other devices. The three resistors, for example R1, R2 and R3, connected in series, and the amount of charge passing through resistor R1 must also pass through resistor R2, and same with R3. Since the charges cannot accumulate anywhere in the circuit. Now we will observe a circuit here. You can see the circuit consists of three resistors in series, R1, R2 and R3. The red arrows shows the direction of the current, while V1 is the voltage across R1, V2 is the voltage across R2, and V3 is the voltage across R3. Now, this circuit represents the equivalent resistance that can be represented by Rs, and here we can see by the direction of current that the equivalent resistance Rs has the same current as the previous circuit was having. And here is the actual photo of a circuit in which all resistors are in series. We can observe here a battery and three resistors having different values. The R1 is having 1 kilo ohm resistor, R2 is consist of 2 kilo ohms, and R3 consists of 3 kilo ohms. Due to this reason, the current I passing through all the three resistors is the same. And according to Ohm's law, if same current passed through different resistors of different values, then the potential difference across each resistor must be different. Let V1, V2 and V3 be the potential differences, or you can say voltages, across each of the resistor, R1, R2 and R3 respectively. Then we can write V1 is equal to I times R1, or V2 is equal to I times R2, and similarly V3 is equal to I times R3. But the total voltage V is equal to the sum of voltages across each resistor. This is very important to know. And we can represent it here like this. You can see that V is equal to V1 plus V2 plus V3. And we can write V1 like IR1. We can write V2 as IR2 and V3 as IR3. Now you can see that I is the common factor among all those. So we take out I as a common factor, and remaining R1 plus R2 plus R3 will be in the brackets that can be replaced by RS. So the final form of this formula will become V is equal to I times RS. And you know that RS is the equivalent resistance that will be equal to R1 plus R2 plus R3. When several resistances are connected in series, the total or equivalent resistance is the sum of the individual resistances. Now here is the example. Calculate the equivalent resistance for the circuit which is connected to 24V battery or 24 volts battery, and also find the potential difference across 4 ohms and 6 ohm resistors in the circuit. Here is the solution. Since the resistors are connected in series, so the effective resistance in the circuit will be equal to 4 ohms plus 6 ohms. That would be equal to 10 ohms. Or we can say that this is the equivalent resistance of R1 and R2 that would be equal to 10 ohms. And the current I in the circuit can be found out by the Ohm's law, that is I is equal to V over R. So by putting the value of V and R, that is the equivalent resistance, 10 is equal to 2.4 amperes. So as now we are having the value of current, we can easily find out the voltage across R1 and R2. So voltage across 4 ohm resistor would be V1 is equal to IR1, and we will put the value of I and R1 and we will get 9.6 volts. While the voltage across 6 ohm resistor V2 is equal to IR1, or you can say IR2 is equal to 2.4 ampere into 6 ohms. That would be equal to 14.4 voltage or volts. Now we have to see resistors in parallel. Resistors are in parallel when they are connected across the same potential difference. So in this case, the total current I that leaves the battery is split into 3 separate paths. Let I1, I2 and I3 be the current through the resistors, R1, R2 and R3 respectively. So due to the conservation of charge, total current in the circuit I is equal to the sum of the currents through each of the 3 resistors. Here we can see the circuit having 3 resistors in parallel, R1, R2 and R3 attached to a battery V, and the red arrows shows the direction of the current. So across R1, I1, across R2, I2 and across R3, I3 are the currents. Now this circuit represents the equivalent resistance that has the same current, same as in series. Here in parallel circuits, we can see that the equivalent resistance has the same current. And this is the actual photo of a resistor in parallel circuit. So battery is connected with 3 resistors that are arranged in parallel. R1 is 3 kilo ohm, R2 is 2 kilo ohms and R3 is 1 kilo ohm. So I is equal to I1 plus I2 plus I3. Since the voltage across each resistor is the same, so by applying Ohm's law to each resistor, we have I1 is equal to V over R1, I2 is equal to V over R2, and I3 is equal to V over R3. Now substituting these values in equation, I is equal to I1 plus I2 plus I3. So we will get I is equal to V over RP. that is the resistance, which are connected in parallel way. So here Rp is the equivalent resistance of the parallel combination of three resistors. Thus, when a number of resistors are connected in parallel, the sum of the reciprocal of the values of resistances of the individual resistor is equal to the reciprocal of the effective resistance of the combination. So 1 over Rp is equal to 1 over R1 plus 1 over R2 plus 1 over R3. The value of equivalent resistance in parallel connection will be lesser than each individual resistance. So household appliances are always connected in parallel so that even if one is switched off, the other devices could function properly. Now, to understand better this concept, here is an example. Calculate the equivalent resistance in the following circuit and also find the current I, I1 and I2 in the given circuit. You can see R1 is of 4 ohms, R2 is of 6 ohms, while the battery is of 24 volts. Now here is the solution. Since the resistances are connected in parallel, therefore the equivalent resistance in the circuit would be 1 over Rp, and by putting the values of the formula 1 over R1 plus 1 over R2, we will have 1 over Rp is equal to 5 over 12 ohm, or we can say that Rp is equal to 12 by 5 ohms. So the resistors are connected in parallel. The potential, or you can say voltage, across each resistor is same. So I1 is equal to V over R1. So by putting these values of V and R1, we have 6 amperes, and I2 V over R2, by putting the value of R2, we are having 4 amperes. Now I is left. So the current I is the total of the currents in the two branches. So if you are having I1 and I2, you can easily find out I by adding them. So I is equal to I1 plus I2 is equal to 6 plus 4, that would be equal to 10 amperes. And in the same way, you can solve the other examples. Here is another example, like calculate the equivalent resistance between A and B in the given circuit. And you can see in the solution that we are going to solve it by parts. So part 1 is consist of 2 ohms and 2 ohms that both are in parallel arrangement. So again, here we will find out first 1 over Rp, or you can say Rp1, that would be equal to 1 ohm. Then in second part, we will find out 1 over Rp2. And the second part is consist of 4 ohms and 4 ohms parallel resistances that are settled down. And you can see the first part we have write it down as the Rp1, that is the equivalent resistance 1 ohms. Now we have to find out the second equivalent resistance, and for that we will use again the same formula 1 over Rp2, that would be equal to 1 over 4 plus 1 over 4. So Rp2 would be 2 ohms. And now we have sorted out two portions of this complex circuit. So now moving towards B, we have the third part, and in third part again we have to find out 1 over Rp3, and Rp3 will be 3 ohms. So now we are having Rp1, Rp2 and Rp3. So by adding them, we will have the total resistance, and that would be 6 ohm. And the circuit became this one. You can say the equivalent resistance between A and B, and that would be what? 6 ohm. So this is the way that you can draw the actual circuit into equivalent resistance circuit. Now we have to see the resistance of a filament bulb. Students, current through a resistor is directly proportional to the potential difference, and the resistance is constant. Such a resistor is called an ohmic conductor. So the current through a filament lamp is not directly proportional to the potential difference. This is because the filament gets hot, which causes the resistance to increase. So at high temperatures, the atoms in the filament vibrate more, and the electrons in the current now collide more with the atoms. So more energy is needed to push the current through the filament. As the potential difference increases, the current no longer increases as much. And here is a brief description of this IV curve, that the resistance of a filament lamp increases as the temperature of the filament increases. So reversing the voltage, or you can say that the negative values on the graph reverses the direction of the electric current but does not change the shape of the curve. So we can conclude here that the lamp does not obey Ohm's law. Now we want to know about LDR, or light dependent resistors. So what are these? A light dependent resistance, or LDR, is also called a photoresistor or cadmium sulfide cell. It is also called a photoconductor. It is basically a photocell that works on the principle of photoconductivity. The passive component is basically a resistor whose resistance value decreases when the intensity of light decreases. So this optoelectronic device is mostly used in light varying sensor circuits and light and dark activated switching circuits. Some of its applications include camera light meters, street lights, clock radios, light beam alarms, reflective smoke alarms, and outdoor clocks. Now these are some projects with the applications of LDR, and that is listed below. The automatic street light circuit, as we have discussed earlier, simple fire alarm circuit, light activated switch circuit, automatic LED emergency light, and night security light. Now this is the LDR structure and its working. You can see the snake-like track shown below in the cadmium sulfide film, which also passes through the sides. And on the top and bottom are metal films which are connected to the terminal leads, and it is designated in such a way as to provide maximum possible contact area with the two metal films. So the structure is housed in a clear plastic case to provide free access to external light. And as explained above, the main component for the construction of LDR is cadmium sulfide, which is used as a photoconductor and contains no or very few electrons when not illuminated. So in the absence of light, it is designed to have a high resistance in the range of mega ohms. So as soon as light falls on the sensor, the electrons are liberated and the conductivity of the material increases. So when the light intensity exceeds a certain frequency, the photons absorbed by the semiconductor give band electrons the energy required to jump into the conduction band, and this causes the free electrons or holes to conduct electricity and thus dropping the resistance dramatically. You can say in kilo ohms. So this is the phenomena that is related to LDR structure and working. Here are some advantages and disadvantages. Like LDRs are cheap and are readily available in many sizes and shapes. Practical LDRs are available in a variety of sizes and package styles, and the most popular size, having a phase diameter of roughly 10 mm or millimeter, they need very small power and voltage for its operation. But there are some disadvantages, like highly inaccurate with a response time of about tens or hundreds of milliseconds. So this is for today. Thank you so much and good luck.